So there's just one more thing that I wanted to introduce you all to today, which is just in the category of max flow is a really cool concept that you should be aware of. And so I wanted to end today with a completely different problem. And this completely different problem is bipartite matching. So this is, so bipartite is a graph where every edge where two categories of vertex. So graph theorists think about bipartite graphs. If you ever are interested in taking the graph theory course, I think there's a discussion in that course of bipartite graph. But there's two categories of vertex. We can call them A and B, and every edge goes from A to B. So this is like here. This is our, right, this is like the A side, and this is like the B side. So in particular, there's like two types of people in the world, and all of the edges are connecting type A people to type B people. That's a bipartite graph. Yeah. And a question that graph theorists ask about bipartite graphs, a classic question in graph theory is, what is the maximum matching? So if I go here and also, I downloaded a better program for next week, and we will see if I can get it working over the weekend. So a question, how many no. Okay, so the matching problem is a classic graph theory problem, and in the matching problem, I've got like 5 A nodes and 4 B nodes, and I'm interested in, okay, let's see, I could go and match up, I could match this person here with that person there, then I could go and match like this person and this person, and then I could go and match like this person and this person. So I've now like matched here, and I've matched here, and I've matched here. So I've now got 3 unmatched people, but there's no edge that goes like from here over to here. Right, there's no edges that connect my unmatched people. So I can't go and like add another matched pair. I can't go and grab another edge. So here I've gone and I have successfully matched 3. So let's see. Another matching is maybe I could go and match, like I could try matching this way, and then I could try matching this way, and this this also gets me 3. 1, 2, 3. Is it possible for me to get 4? So maybe I try matching these two this time, and I go and match these two, and then I go and match these two, aha, and now I figured out a way to get 4. So there was a lot of like trial and error in figuring out, can I match 4, or can I, the way the edges line up, am I only able to match 3? So does this problem make sense? Um, okay. So anyway, this is just a classic graph theory problem. And the reason that I wanted to illustrate this is it's without a lot of trial and error, it's not completely obvious how you would go and figure out what are the most pairs of people that you could match. And so if like, again, maybe like a classic example of this is maybe you have singers and songwriters. So in order to make a hit, I need both a like music and lyrics. So if I have like 5 people who can produce lyrics and 4 people who can produce melodies, and these lines connect people who are able to work together. You know, this person's like a bit of a prima donna, and so like only this individual is able to work with them. And so like you might be interested in like how many singer-songwriter pairs could I make with this configuration of industry professionals, or, you know, like make up your own practical application. But one reason I wanted to illustrate this is because it turns out that this is a case where we can think of this as a max flow problem. If I just go and add an imaginary vertex, so this is a so I'm going to go and add an imaginary source and sink. So this is a source, A. This is a source A, and this is a sink B. Maybe I. Yeah, I'm hopeful that I will get working a better program by next week. So if I go and add these imaginary extra nodes to my graph, and then I go and draw some lines like, can I get a different color? Yeah, so well, let's just do this with a brush. So what I've done is I had my original graph, and I'm now going to go and take a source A and connect it to all these the type A people. And then I'm going to take a sink B and connect it to all of the type B people. And now I'm trying to push as much flow as possible from A to B. And I can go and like write capacity 1 on every edge. So let's just go and write capacity 1 on every edge. And so what this capacity 1 does is it says, I can only use each type A person once because each type A person can only get 1 unit of flow. And each type B person can only get 1 unit of flow. And then, so every time I push flow from A to B, I must be going and matching up an A person to a B person, and the capacity constraints tell me that I'm not going to use the same A person twice, because I can't use this A person twice because this A person can only get 1 token from the source. Anyway, the questions about this problem. This problem isn't vitally important, but I just wanted to throw this up here as an example. Again, you may not be in a position where you need to make like singer-songwriter pairings, but this is a way that you can use our max flow machinery to solve something that doesn't seem like a max flow problem. It doesn't seem like producing music with singer-songwriter pairs is something that's necessarily a flow problem, but you can go and add a little bit of extra structure to the graph to make that work.